My name is Zlatan Ajanović, and I'm presenting you our work titled Robotic Packaging Optimization with Reinforcement Learning. We treat the problem of food from food packaging industry, where the machine is packing the products into the boxes using robots. One such machine looks like this, where several Delta robots pick the products from a product belt and place them into the box. The problem can be schematically represented as such. Here we have first our box belt and several boxes moving on the belt. Then we have our product belts, which transport several products in parallel to the box belt. And we have several robots that are packing different products and placing them into the boxes. Our vision system has a limited view horizon, and then based on the input, assigns different products into different boxes. So one example looks like this. So we have a box which is shown in orange, and we have a constant product supply. We can assign different products to be placed into this box. However, sometimes it happens situation that we have a varying product supply, and that the fulfillment of some box actually is not possible, is impossible to happen. And we have the boxes which leave the box belt, which are not fully filled or not filled at all. For this, our goal is to optimize box belt speed such that these situations do not happen, and that we can predictively slow down box belt such that we can fill all the boxes. So the question is how to optimally control the speed of box belt. Our goal is that we have at least 99.8% of the products placed in the boxes. Then box quality must be 100%, meaning that all the boxes that leave the box belt must be 100% filled. Our research goal is to improve the current heuristic or rule-based engineered solution that is reactive and corrects in the case of situation that some boxes cannot be filled, and in that case also does not fulfill all the requirements, with some data-driven solution that can predictively prevent such situation occurring at all. And in this case, we have fulfilled requirements. So going for our methodology, we use reinforcement learning, where agent has the objective to maximize the number of placed products while satisfying all the constraints as requirements set before. We formulate constraints with the penalty functions, and our reinforcement learning works in a control interacts with the environment that is consisting of simulator that simulates all the dynamics and all the processes in the machine, plus the control scheme of the packaging machine. We have our actions and our state and reward coming from a system. On a real machine, our action is a box belt speed, VB, and we formulate rewards based on the lost boxes, so that we penalize each box that is not fully filled, leaving the box belt, and all the products leaving the product belt that are not filled into the boxes. Our state features are represented by first feature is the first box that is not assigned with some products. Then the products that are not assigned to any box, 2 of them, and inflow on both tracks, as well as our box belt velocity and past box belt velocity. To addition to this, we also add some history. So looking into real time, when we have actions and states and reward represented like this, we actually can notice drastic product loss. Why this happens? So if we have a constant box velocity and we see in orange box and products that are assigned to this box, we can see that they are well aligned, that they can be picked by a robot and placed into the box. However, if we change velocity, in this case, if we increase velocity, our box is already leaving before the products are in the reach of the robot to be placed into that box. And the original assignment is invalid. We modify our loop, reinforcement learning loop, then by adding a design delay such that this delay actually slows down reinforcement learning actions and allows actually robot, so the machine control scheme to fulfill all the planned assignments. Additional to that, we also add the constructed future state and reward so that we match the delay and minimize the impact of that on the reinforcement learning agent. If you look now at the example with the constant velocity, we can actually modify box belt velocity, but we delay this modification such that all the boxes, all the products that are already in the horizon and the assigned products are not influenced by the action. This approach is similar to Smith predictor in a control systems. If you look into the results, both reinforcement learning and baseline actually fulfill box quality. However, if you look at the products placed and the requirement that this is higher than 99.8%, our baseline is not fulfilling this requirement. It loses 0.69% of the products, but our reinforcement learning agent loses only 0.06% of the products, which means that we reduce the lost products in 90%. If you look at the comparison on the real world data, this is one scenario where actually baseline solution loses 30 products. And as you can see here in the orange, our reinforcement learning agent does not lose any product. You can see in a close-up here that actually our agent 6 seconds in advance slows down a little bit box belt and as such reacts predictively. If you look in this on this example, you can see here that baseline solution moves constantly, but then slows down drastically. And our agent actually slows down in advance, and smaller correction in velocity actually achieves the same effect. This means that actually our learned predictive behavior prevents this critical situation where you can see that a baseline solution has drastic slowdown. As a conclusion, our approach learns predictive behavior for problem prevention. So it predictively slows down when needed, such that it doesn't have to behave correctively. It is compliant with the industry requirements and it exceeds baseline with improved productivity, smoother control, and reduced code execution. Our contribution is a reinforcement learning solution that is appropriate for a real robotic problem in the food industry, but it can also be adjusted to different industries. Our RL solution for the policy inference can be used for using in the highly complex control schemes where we want to minimize interference with the rest of the control scheme. And we also show the validation on a real data coming from logs from real machine. Thank you very much.